Hello, I'm Kazuki Nakamura from Hiroshima State University. I'll explain throughput characteristic evaluation of media access control SPMAC in multi-op wireless LAN environment considering capture effect. First, I'll explain the background and the purpose of this study. In the current Internet service, the wireless LAN based on IEEE 802.11 is one of the important access networks. Here, wireless LAN usually uses CSMA/CA for media access control. This method tries to avoid data frame collision using the random back-off time is obtained by contextual window. However, it is known that the data frame collision often occurs among the wireless terminals when the number of terminals increases. If the collision occurs, the back-off time increases twice as large as its previous value. Then the total throughput decreases. Therefore, we have proposed a new media access control method based on the synchronization phenomena of coupled oscillators. We refer to this method as SPMAC. In our previous study, we confirmed that SPMAC can avoid the data frame collisions and improve the throughput in infrastructure mode. On the other hand, SPMAC increases data frame collision when the hidden terminal occurs in multi-op wireless LAN. Thereby, the total throughput decreases. But when frame collision, a frame error may not occur. If the difference in the received signal strength is high, the frame may be received normally at the time of collision by capture effect. So we evaluate throughput characteristic of SPMAC in multi-op wireless LAN environment considering capture effect. Now, there are several kinds of mathematical models of synchronization phenomena. In this model, the most famous model is the Kumamoto model, and SPMAC uses it. The Kumamoto model is obtained by this equation, and it indicates the ith oscillator's phase when there are n coupled oscillators. This model assumes a situation where each oscillator runs independently at its own natural frequency and interacts with all other oscillators. In this model, theta shows the phase, omega indicates the natural frequency, then large K shows coupling strength, and this means how strong each oscillator tends to synchronize. Finally, large N indicates the number of oscillators. Next, I explain the detail of SPMAC mechanism. SPMAC uses the synchronized phase based on the Kumamoto model for setting the back-off time instead of using a random integer in CSMA/CA in order to avoid the overlap of the back-off time among terminals. However, if the phase completely synchronizes, the collision occurs continuously. Thus, we use the case when all oscillators synchronize with phase shifting, that is, each phase shifts a certain period. Additionally, SPMAC applies one of oscillator's phase to each terminal. From this equation, in CSMA/CA, the back-off time is obtained by a random integer. On the other hand, SPMAC sets the back-off time using cosine value based on synchronized phase. Here, in this equation, large N and alpha mean the number of terminals and coefficient for normalization. In the next slide, I'll explain how SPMAC uses the cosine values. This figure shows an example of cosine of synchronized 3 oscillator with phase shifting. From this figure, when all oscillators synchronize with phase shifting, each oscillator has different cosine at time t. Furthermore, when a certain time passed, the relation of cosine changes. Therefore, SPMAC can avoid the overlap of back-off time and set fair value by using phase shift cosine value. Now, this method is kind of same as applying the time slot of TDMA to CSMACA. Next, I'll explain what is the capture effect. The capture effect means a phenomena even if the collision occurs, receiver can receive data correctly depending on the signal strength ratio between required data and interference. For example, let's assume that there are topology of a linear multi-hop network. In this situation, it is assumed that the distance between wires node 1 and wires node 2 is shorter than the distance between interfering wires node n. Here, wires node 2 sends data frame to node 1. Wires node n outside the carrier sense range sends data at the same time. If each node sends data simultaneously, the collision occurs. However, if the distance between wires runs are enough long, data 1 is received successfully by node 1 because signal power of data 1 is enough larger than interference by data 2. And same result can be obtained against data which the wires node n sends. To summarize, if the signal strength is enough larger when collision occurs and then data transmission succeeds, we call this phenomena as the capture effect. This figure shows simulation model of this study. This study used the chain topology of multi-hop wireless LAN placed on a straight line at a certain distance. This figure shows simulation model of this study. This study used the chain topology of multi-hop wireless LAN placed on a straight line at a certain distance. We simulated by changing the number of send terminals and relay terminals, the distance between terminals. We compared CSMACA and SPMAC. In this evaluation, we evaluate total throughput and the number of collisions. Next, this table shows the simulation parameters. We use network simulator NS2. A wireless LAN environment is IEEE 802.11g. The communicable radius is 10 meter. The carrier sense radius is 20 meter. The capture ratio is 3. And transport protocol is UDP, and simulation time is 60 seconds. In this evaluation, the simulation result showed the average of 10 trials. Here, in SPMAC, we use these parameters. By using these parameters, all oscillators can synchronize phase with phase shifting. This figure indicates the total throughput when the number of send terminals is 1. X-axis shows number of relay terminals and distance between the terminals, and Y-axis shows total throughput. From this figure, found that SPMAC can obtain slightly higher throughput than CSMACA. Especially, even if collision occurred by hidden terminal, packets can be received normally by capture effect because the distance is long. Here, since the average back-off time SPMAC is smaller than CSMACA, SPMAC can obtain the merit of capture effect than CSMACA. This figure indicates the total throughput when the number of send terminals is 5. The x-axis and y-axis are the same as the previous graph. When the terminal is within the carrier sense range, total throughput of SPMAC is higher than CSMACA even if send terminals increase. On the other hand, when hidden terminals occurs, the effect of throughput reduction due to data collision is greater than the throughput improvement obtained by the capture effect. Therefore, SPMAC cannot obtain higher throughput than CSMACA. This figure indicates the number of collisions when the number of sent terminals is 1 and 5. X-axis shows the number of relay terminals and distance between the terminals, and the y-axis shows the number of collisions. From this figure, we found that SPMAC reduces the increase of collision even if the number of terminals increases when the number of relay terminals is 1 and 2 at 5 meters. Also, data frame collision rapid increases due to the hidden terminal problem occur. This figure indicates number of received packets by capture effect when the number of sent terminal is 1. X-axis shows the distance between the terminals and the number of relay terminals, and the y-axis shows that left axis is the received packets by capture effect, and the right one is the ratio of received packets by capture effect to all collision packets respectively. From this figure, correlation can be seen between two graphs, collision and capture effect. In proportion to the collision, received packets by capture effect are increasing. Because, although it is expected that data frame collision increases due to hidden terminals, the difference of the received power is small because of relatively short distance. Therefore, ratio of capture effect does not increase. This figure indicates number of received packets by capture effect when the number of sent terminal is 5. From this figure, we found that probability of packets received by capture effect is higher than CSMA-CA due to characteristic of SPMAC and capture effect, but the advantage of SPMAC decreases due to collision by hidden terminals. From this reason, SPMAC cannot obtain a significant improvement in throughput. Finally, I summarize my presentation. We evaluate throughput characteristic of SPMAC in match-up wireless LAN environment considering capture effect. By simulation evaluations, we confirm that total throughput almost higher than CSMA-CA in bidirectional UDP communication. From a point of view of capture effect, packets that successfully received are increasing by capture effect, but the benefit of capture effect is limited due to packet collisions. That concludes my presentation. Thank you.